Video, we're going to be looking at the PC in a little bit of closer detail. So let's go ahead and take a look in there. So the PC, one thing I should mention at first is that although it might intuitively make sense to start at instruction 0 when we start the computer, we're actually going to start at instruction 7. So on the first rising edge of the clock, we get to instruction 0. So we have a logic 1 on the clock for instruction 0, which will be important when we talk about the register file, actually. But just trust me on that for now. That is helpful. So the way that I've made my program counter is I have a present state module and a next state module. The present state module is actually very simple. It tells us basically at what value the program counter currently is. And so since we have a 3-bit program counter, we can actually count from 0 up until 7, which corresponds to the instructions 0 through 7 that are in the instruction memory. But so they're just 3 flip-flops, basically, in parallel that could get updated on clock cycles with this clock signal fed in from the next state module with these inputs. And then we don't really use the Q bar outputs on the flip-flops, but we do use the Q bar or the Q outputs, which feed basically to the output of the program counter. So with the present state, we just store what state we're in right now, and that gets updated using this clock signal. The next state is where things kind of get interesting, and so I basically worked out on with a pencil and paper the basically the necessary logic for present state 0 or present state bit 0 to next state bit 0. So if present state bit 0 is actually I'll just say with the 0th bit of the state, it's just an inverter. And you'll notice I have slow inverter buffers basically on each present state to next state line because the program counter needed that added delay to work properly. But so ostensibly all that present state bit 0 does is inverts, and that's enough to generate the correct next state bit 0. For present state bit 1, it's a little bit more complicated. We first have to, this is an XOR gate. In case you were wondering, the symbols are a little weird. But we actually have to XOR present state bit 0 with present state bit 1, and then that output actually gets put through a slow inverter buffer to generate next state bit 1. So from present state bit 1 to next state bit 1 is just XORing present state 0 with present state 1. That's how we calculate next state 1. Present state 2 is the really interesting one. So there's 2 things working in parallel here. First, present state bit 2 has to be XORed with present state bit 0. And then also present state bit 1 has to be inverted. Yeah, this is an inverter here, down here. Has to first be inverted, and then we have to AND present state bit 2 with the NOT of present state 1, basically. So then another thing we have to do is actually take this output of the XOR of present state 0 with present state 2, and we have to AND it with present state 1. Now, those 2 output bits that we calculated here then get put through an OR gate, which is then enough to basically produce next state 2, but then we put it through the 2 slow inverter buffers to make sure the timing's all correct. And again, I worked this out on pen and paper, basically drawing a truth table with these as my inputs, my present state bits, these as my outputs, my next state bits, and then doing a K-map, reducing logic, etc. So that was the interesting block there. So present state just flip-flops with the clock, tells you loads in next state on the clock edge, so that we can then read the next state out on the output, and then the next state module just calculates based on what the current present state is, what the next state needs to be. So if the present state is 0, the next state will be 1, present state is 1, next state will be 2, so on and so forth, and out just goes 0, 1, 2, 3, 4, 5, 6, 7, and then it actually wraps back down to 0. That's an important point to note. And this is all rising edge triggered, and I think that's enough for the program counter. This will be useful for the ROM instruction memory in the next video.